I want you to try and imagine a seemingly impossible engineering challenge.
Oh, those are always the best kind.
Right. Okay, so let's say you've just been handed the schematics for this revolutionary, highly complex airplane wing.
Okay, I'm picturing it.
And your objective is to know with, like, absolute certainty how that specific aerodynamic profile will react to violent, turbulent shears.
Oh, wow.
Yeah, or massive pressure differentials and thermal shock from sub-zero altitudes.
That is a lot of variables to juggle.
Exactly. But here is the massive catch to this assignment. You have to know every mathematical detail of its physical behavior before a single sheet of aluminum is even milled.
Right, before it even physically exists.
Yes. You have to prove it works before you build it.
It's really the ultimate paradox of modern engineering. You're tasked with predicting the definitive physical behavior of an object that does not yet exist.
Right.
And you're doing it using nothing but theoretical mathematics and computing power.
And doing that successfully is the core mission of our deep dive today. We are exploring the philosophical framework and, the mathematical mechanisms that engineers rely on to translate our chaotic, continuous reality into solvable, discrete chunks.
It's a fascinating process.
It really is. We're looking at this amazing lecture covering mathematical modeling and what's called the Finite Element Method.
Yes, the FEM.
But rather than just walking through differential equations on a dry chalkboard, which, nobody wants to listen to.
Yeah, that's not exactly great audio content.
Exactly. We are going to explore the underlying philosophy of how we, as humans, fundamentally comprehend complex physical reality.
Because the overarching philosophy behind this entire discipline, it requires a pretty profound shift in perspective.
How so?
Well, it begins with this rather humbling admission that reality is simply too complex to solve directly.
Okay, so we just admit defeat right out of the gate.
Kind of, yeah. Absolute perfect calculation of the physical world is a fool's errand. Therefore, mastery in this arena doesn't come from calculating every single atom.
Right.
It comes from knowing the precise mechanics of approximation.
Okay, let's unpack this. Because before we can even simulate our airplane wing in a computer, we have to talk about how we view reality itself.
Right. And in the source material we're looking at, the professor breaks down this translation process. He starts with what is termed the real problem.
The real problem, capital R, capital P.
Exactly. The real problem is the actual physical world. It's the airplane wing flying through a literal storm.
Right.
And because the physical universe contains infinite variables.
Like what kind of variables?
Oh, ambient humidity fluctuations, microscopic material fatigue, subtle temperature gradients.
Just a million tiny things.
Infinite things, really. Because of that, the real problem is fundamentally intractable. You cannot run a mathematical equation on infinity.
Right. That makes sense. It actually reminds me of how we deal with digital media.
Oh, like audio files.
Yeah, exactly. When you compress a massive uncompressed raw audio file into an MP3, you aren't perfectly recreating the studio recording.
You're losing data.
Right. You're algorithmically stripping out the acoustic frequencies that the human ear physically cannot perceive anyway.
Oh, that's a great point.
You deliberately throw away massive amounts of real data just to make the file mathematically manageable. But to the listener, the song sounds identical.
Exactly.
The utility of the MP3 comes directly from the data you strategically choose to ignore.
That is a brilliant way to frame it. Because the simplified model in our source material, it acts exactly like that audio compression.
Right.
We make calculated assumptions. We strip away the microscopic noise that doesn't dramatically alter the macro mechanics of the structure.
So we drop the stuff that doesn't really matter for the big picture.
Right. We move from a messy physical object to a clean conceptual baseline. And once we establish that simplified model, we apply governing mathematical laws to it. Things like the Navier-Stokes equations for fluid dynamics,
Right.
or fundamental thermodynamic laws.
Okay.
This generates our mathematical model. But what's fascinating here is the psychological trap engineers have to avoid.
A trap.
Yeah, because when you are crunching these massive matrices, you are not actually calculating reality.
Wait, really?
Really, you're only calculating the behavior of your own assumptions.
Oh, wow. So if I'm simulating a massive structural load on this wing, and the math tells me it holds up perfectly,
Yeah.
the math is only validating the parameters I had the foresight to include in the first place.
Exactly. If you fail to account for, say, a specific harmonic resonance, the model might show a perfectly stable wing.
While the physical version just gets ripped apart in the sky.
Exactly. And that is the exact tension that keeps aerospace engineers awake at night.
I can imagine.
The model is only as robust as the assumptions it's built upon. So to mitigate that risk, engineers anchor their models to the fundamental, unyielding physical laws of the universe.
Right.
And when you strip away all the complexity, the mathematical models we use to describe engineering or physics or chemistry, they ultimately resolve into three fundamental states of reality.
Okay, let's trace the life cycle of our airplane wing through those three states, because it completely changes the way you perceive the forces acting on the objects around you.
It really does. So the first state of reality we model is called the boundary value problem.
Boundary value. Okay.
Conceptually, this is the philosophy of equilibrium. It describes a system that is dependent on its position in space, but completely independent of time.
Independent of time. So if our airplane is just like sitting idle on the tarmac on a sunny day.
Precisely that. The sun is heating the top of the wing, and the shadow is keeping the underside cool.
Right.
Eventually, the thermal transfer through the aluminum reaches a steady state. The temperature at any given millimeter of that wing just stops fluctuating.
Okay, so if you measure a spot on the leading edge, it might be exactly 40 degrees.
Right, and it will stay 40 degrees regardless of how long you wait.
Yeah.
The thermal solution only changes based on where you are on the wing.
Your spatial coordinates.
Exactly. Not the time on the clock. That is a boundary value problem. A stable, time-independent reality.
But obviously, the airplane isn't going to sit on the tarmac forever.
Hopefully not.
Right. The engines spool up, the plane accelerates down the runway, and suddenly the physical forces acting on the wing are changing rapidly.
Which brings us to the second mathematical state, the initial value problem.
Okay, so we're adding time back in.
Yes.
Yeah.
This is the mathematics of propagation, where we add that critical dimension of time back into the matrix. This governs the transient state.
The transient state.
Yeah, the moment the plane takes off, the air friction increases, the atmospheric temperature drops, and aerodynamic lift begins warping the structure.
So the forces are actively traveling through the material.
Yes, the stress and thermal loads are actively propagating. If you run a calculation on the wing root at minute 1 of the flight, the structural stress value is completely different than at minute 5 when it reaches cruising altitude.
Okay, that makes total sense.
The mathematical solution requires integrating both the spatial coordinates and the time elapsed. It's a very dynamic, fluid reality.
So we have the boundary value for the steady state and the initial value for the journey or the transition.
Correct.
But neither of those really accounts for a catastrophic failure. Like, what happens when the plane hits a massive pocket of turbulence and the wing bends way beyond its normal operating parameters?
That introduces the third and most complex state,
Which is
the eigenvalue problem.
the eigenvalue problem.
Right, this is the philosophy of stability. It represents a sudden, critical shift in the nature of reality itself.
Wow, okay.
To understand the mechanism here, we have to look at the concept of equilibrium energy states.
Right, because the lecture talks about stability in terms of like columns bearing loads.
It does.
But let's look at it through the lens of potential energy to stick with our wing.
Good idea. So, when our airplane wing is flying normally, it bends slightly upward due to aerodynamic lift.
Yeah.
It is in a state of stable equilibrium. If a mild gust of wind pushes it further up, the internal stiffness of the aluminum acts as a restorative force.
It wants to snap back.
Exactly. It pulls it back to its original position once the gust passes. The structure inherently seeks its lowest potential energy state.
Okay.
But the eigenvalue problem mathematically models the breaking point, what we call a bifurcation point.
Because, I mean, if we take a perfectly straight structural column inside that wing,
Okay, yeah.
and we apply a massive compressive force directly down its center axis, theoretically it shouldn't bend, right? If the force vector is perfectly straight down, it's just compressive stress. The material should just pack denser and denser until it basically crushes.
In a pure theoretical vacuum, yes, the column would just compress forever. But in the physical world, the mechanism of failure is bifurcation.
Bifurcation.
Yeah. As the turbulent load on the wing increases, the potential energy inside that internal column builds exponentially.
Like a coiled spring.
Exactly like that.
Yeah.
The column is technically still in equilibrium, but it has become an incredibly fragile, high-energy equilibrium.
So it's mathematically primed for chaos.
Exactly. And at a very specific mathematical threshold, the critical eigenvalue, this system reaches a fork in the road.
The breaking point.
Right. The slightest physical imperfection in the aluminum alloy or maybe just a microscopic vibration from the engine, creates a tiny lateral force.
Oh, wow.
Instantly, violently buckling outward becomes the lower energy state for the material. The column snaps from stable equilibrium into unstable equilibrium.
And the geometry of the structure is permanently altered. The math resolves to a completely new shape.
Yeah.
It's not just a gradual bending, it's a catastrophic shift in the governing physics of that object.
And engineers must be able to calculate that exact critical eigenvalue to ensure the wing never reaches that bifurcation point under any foreseeable flight conditions.
Which brings us to a massive philosophical wall, really. The crisis of calculation.
It is a huge crisis.
Because we use differential equations to map out these three states, right? The steady tarmac, the transient flight, and the catastrophic buckling.
Right.
But differential equations represent a continuous universe. They draw smooth, infinitely divisible curves of space and time.
Yes, that's calculus.
But computers, they do not process continuous infinity. A microprocessor operates on discrete logic. It uses finite matrices.
Exactly, ones and zeros.
So how do we force a continuous physical universe into a discrete mathematical machine?
That was the defining hurdle of 20th century computational physics. The early attempt to bridge this gap was a mathematical trick called the finite difference method.
Finite difference.
Right. Since a computer cannot integrate an infinite number of points along a smooth aerodynamic curve, engineers translated continuous calculus into discrete algebraic equations at very specific predetermined points.
Okay, so if we connect this to the bigger picture, this is basically the strategy of throwing a rigid coordinate grid over your engineering problem.
That's a perfect visualization.
Instead of calculating the infinite space between the lines, you only calculate the algebraic values exactly where the lines intersect.
Right, you reduce continuous infinity to a highly dense, manageable set of dots.
But here's where it gets really interesting.
Okay.
If I overlay a massive grid of, let's say, 1,000,000 tiny square pixels on the leading edge of a curved airplane wing, I can just brute force the calculation, right?
And so?
Yeah, I just crank up the computational resolution until the grid accurately represents the curve.
You would naturally assume that, but mathematically, it's a disaster.
Really? Why?
When you force a rigid square grid over a sweeping aerodynamic curve, you inevitably create a stair-step effect at the boundary.
Oh, like a pixelated image.
Exactly like that.
Yep.
Your grid generates thousands of tiny, jagged 90-degree corners that just do not exist on the actual physical wing.
Because the computer only knows what falls precisely on its grid lines. It doesn't know there's a smooth curve connecting them.
Right. And the mechanism of failure here is that in structural engineering, sharp corners concentrate stress.
Oh, I see.
So your computer model begins calculating massive phantom stress fractures at every single one of those jagged stair-step edges.
Wait, phantom forces?
Yeah, they aren't real. But those phantom forces cascade through the algebraic equations, completely corrupting the entire model.
That's crazy.
The finite difference method fundamentally fails when confronted with a complex, chaotic topology of the real world.
So aerospace engineers in the 1950s hit a brick wall.
A massive one.
Companies like Boeing were trying to design these swept wings and intricate fuselages for the jet age, and the math just couldn't keep up.
No, it couldn't. And without viable computer models, the only alternative was physical testing.
Which more is building it.
Yeah. You had to machine a highly precise scale model of the wing out of steel, mount it inside a wind tunnel, and blast it with air.
That sounds expensive.
Incredibly expensive. And if it sheared apart, you had to analyze the wreckage, alter the blueprints, machine a brand new model, and try all over again.
Wow.
It was an agonizingly slow process. It just couldn't sustain the pace of the Cold War aerospace race.
So they needed a completely new philosophy.
Desperately.
And that necessity birthed one of the most important conceptual breakthroughs in modern engineering, which is the finite element.
Yes. The paradigm shift arrived in a 1956 paper. It was authored by a team of 4 aerospace engineers: M.J. Turner, Ray W. Clough, H.C. Martin, and L.J. Top.
Okay.
Their genius was a complete inversion of the previous approach.
How so?
Instead of trying to force a rigid, uniform grid on top of a curved shape, they conceptually shattered the geometry of the wing itself.
Oh, wow. So they didn't map the wing. They built the wing out of mathematical shards.
Exactly. They broke the continuous geometric profile down into thousands of discrete, simple shapes.
Like what kind of shapes?
Primarily triangles and quadrilaterals. And they called these individual pieces elements.
Okay, finite elements.
Right. And this completely solved the stair-step problem. Because you aren't bound to a rigid grid anymore, You can use a technique called a variable density mesh.
Variable density, meaning you can change the size and shape of the pieces depending on where they are.
Precisely. On the wide, flat middle section of the wing, you can use large, simple elements.
Because nothing crazy is happening there.
Right. But as you approach the highly curved, complex leading edge, you densely pack thousands of tiny, dynamically skewed triangles that conform perfectly to the aerodynamic surface.
So you map the topology with absolute fidelity, no jagged edges?
Exactly.
But I'm trying to picture this. How do those disconnected triangles actually simulate a solid object?
That's the magic of it.
Like, if atmospheric pressure is pushing violently against the tip of the wing, how does the mathematical model transfer that force down the structure to the fuselage?
Right.
What is the actual mechanism making these discrete shapes, talk to each other?
The mechanism lies in the corners of the triangles. Engineers call these nodes.
Nodes. Okay.
The elements are mathematically stitched together because they share node coordinates.
Let me make sure I'm following. Let's say triangle A is at the wingtip, and triangle B is right next to it.
Right.
They share two nodes, basically a common edge.
Exactly. And when the computer applies an aerodynamic force vector to triangle A, it uses a massive stiffness matrix to calculate exactly how that force displaces triangle A's nodes.
Oh, and because triangle B is mathematically locked to those exact same nodes,
You got it.
the displacement of A instantly becomes the input force acting on B.
Yes. The computer solves an enormous system of simultaneous linear equations.
Wow.
It calculates how the mechanical energy cascades from node to node, element to element, rippling across the entire structure in a highly accurate simulation of solid mechanics.
That is incredibly elegant.
It really is. You are solving the macrostructure by perfectly resolving the micro interactions of its finite pieces.
But I imagine the original 1956 paper outlining this was, well, incredibly dense, right?
Oh, absolutely. It was highly theoretical matrix algebra. Most practicing engineers struggled to apply it at first.
So how did it become the industry standard?
Well, it was revolutionary, but relatively inaccessible. The true democratization of the concept happened a few years later.
Okay.
In 1960, at a conference in Pittsburgh for the American Society of Civil Engineers, Ray W. Clough, one of the original authors who was then a young professor at UC Berkeley, he presented a new paper.
What did he do differently?
He simplified the complex aerospace matrix methodology specifically for two-dimensional plane elasticity problems. He made it digestible for the broader engineering community.
Oh, nice.
And in that presentation, he officially coined the term that defines the industry today, the finite element method.
The finite element method. So what does this all mean for you listening today? Why does the history of mathematical modeling matter to someone who isn't, designing jet aircraft?
It's a fair question.
It matters because by conceptualizing how to break a continuous surface down into finite elements, those engineers created a universal master key for physical reality.
They really did.
They created a philosophy that allowed humanity to simulate the behavior of almost any structure inside a microprocessor before it even exists in the physical world.
The applications are virtually limitless. Automotive engineers use finite element meshes to simulate exactly how a car frame will crumple and absorb kinetic energy during a high-speed collision.
Oh, wow, to optimize the chassis and protect the cabin.
Exactly. Civil engineers simulate how the complex steel skeleton of a skyscraper will damp the resonant frequencies of a massive earthquake.
That's incredible.
Biomechanical engineers even use it to model the complex, nonlinear elasticity of human arteries to design better cardiovascular stents.
It's profound when you zoom out and look at the conceptual journey we've taken here today.
It is a huge leap.
We started by exploring the fundamental philosophy of modeling reality. We accepted that the physical universe is too chaotic to solve directly.
Right, so we rely on the power of the simplified model, stripping away the noise like an audio codec.
Exactly. And from there, we mapped those models onto the three states of reality governed by differential equations.
The steady equilibrium of the boundary value problem, the dynamic propagation of the initial value problem, and the catastrophic bifurcation points calculated by the eigenvalue problem.
Right. And finally, to translate those continuous mathematical states into the discrete logic of computers, we abandoned the flawed, jagged grids of the finite difference method.
We learned to conceptually shatter reality into discrete finite elements, linking them node by node to simulate the physics of a solid universe.
The modern infrastructure of human civilization is entirely reliant on this philosophical leap. The safety and efficiency of the built world hinges on the mathematical premise that the infinitely complex can be mastered, provided you know exactly how to divide it into finite, solvable pieces.
It really is a triumph of approximation.
It absolutely is. But I want to leave you with a final provocative thought, something to explore long after this deep dive is over.
Ooh, I love these.
We've established that engineers invented the finite element method as a clever computational hack, right? It was a mathematical workaround to force discrete silicon chips to process a continuous flowing universe.
Right, a brilliant shortcut.
But what if they accidentally stumbled onto a fundamental truth about the nature of the cosmos itself?
Oh, wow. That raises an important question about the very foundation of physics.
Right, because if you dive into quantum mechanics, theories suggest that at the Planck scale, the universe might not be a continuous, smooth fabric.
Right, the idea of quantization.
Exactly. Energy and perhaps even space and time themselves might exist in discrete, indivisible chunks, quanta.
That is mind-bending.
So the next time you look up at an airplane slicing through the clouds or you drive across a massive suspension bridge, ask yourself this. Did engineers just invent a brilliant way to simulate a continuous reality? Or is the universe itself, at its most fundamental quantum level, just the ultimate, perfectly assembled finite element model?